Bismillahirrahmanirrahim. Today we are going to start chapter number 25, which is about capacitance. We will study capacitors in this chapter. Physics provide us understanding of basic sciences of practical devices which are in human use. This chapter is mainly about capacitor, a device in which an electrical energy is stored. The energy used in camera's flash unit is stored in a capacitor. Normally, a battery unit provides energy at some modest rate when the flash unit is triggered. However, once the capacitor is charged, it can supply energy at a greater rate when the flash unit is triggered. So, provide enough energy that the unit emits a burst of bright light. So, a capacitor is a device that stores electrical potential energy and electric charge. To make a capacitor, just insulate two conductors and transfer charge on the conductor to make them positive and negative. Work must be done to move the charges through the resulting potential difference between conductors, and the work done is stored as electric potential energy. Capacitors are used widely in electrical appliances under our use, such as fan, electronic flash units for photography, pulse lasers, airbag sensors for cars, radio and television receivers, and many others. The physics of capacitor can be generalized to other cases, like Earth's atmospheric field is also a huge spherical capacitor, and that partially discharges via lightning. So the basic elements of any capacitor consist of two isolated conductors of any shape. Here I am drawing a more general configuration of a capacitor called as parallel plate capacitor. The distance between the two plates is d. This one is the top side of the bottom plate, which has charge minus q. This one is the bottom side of top plate having charge plus q. The symbol used for the presence of capacitor in a circuit is also based on parallel plate configuration and used for all the geometries. This is the symbol. You can also draw it in this form. This is positive charge plate and this is the negative charge plate. Field lines travel from positive towards the negative plate. This is a parallel plate capacitor made up of two plates of area A separated by a distance d. The charges on the facing plate surface have the same magnitude q but opposite signs. The field lines show the electric field due to charged plates is uniform in the central region between the plates, and the field is not uniform at the edges of the plate as indicated by the fringes of the field lines here. So when the capacitor is charged, its plate acquire charges of same magnitude but opposite sign. We take absolute value of these charges Q is not the net charge. So capacitor plates are conductors and the value of potential is same at all points on the surface of the conductor and considered as the equipotential surface. For historical reasons, the change in potential is represented by V, not by delta V as we use in the previous chapter. Then the charge and the potential difference V for a capacitor is proportional to each other. So Q is proportional to V and Q is equal to CV. The proportionality constant is called the capacitance of the capacitor. The capacitance depends on the shape and size of the conductors and on the nature of the insulating material between them. The unit of capacitance is farad. So, a simplest way to charge a capacitor is to use battery with proper circuitry. I am drawing the same configuration, a parallel plate capacitor like this one. Here a battery is represented by this symbol. Terminal of higher potential is labeled as positive and called the positive terminal of battery. Terminal of lower potential is labeled as negative terminal. A switch S is used to open and close the circuit. Capacitor is based on two metal plates H and L which are connected to the battery. And so here again this plate L is connected with electric wires and goes from switch S to the negative terminal of the battery, and this plate H is again connected with electric wire and goes to positive terminal of the battery. So now it forms this whole configuration makes a circuit. The battery maintains the potential difference between its terminal. The present circuit is not complete because switch S is open and the path is disconnected. When the switch is closed, let's move it here, now it is closed, it will connect the wires electrically and complete the circuit. We know that charges can flow in a conductor. When the circuit is completed, electron will move through the wires by an electric field that the battery sets in. The field moves electron from capacitor plate H to the positive terminal of the battery, making H plate electron deficient, or this plate H becomes positive charge plate. Similarly, the field drives the electrons from negative terminal of the battery to capacitor plate L, and plate L gains negative charge. So the potential difference is 0 when the plates are uncharged. As the plates get charged, the potential difference increases until it equals the potential difference between the terminals of the battery. Now plate H and positive terminal of the battery are at the same potential. Similarly, negative plate L and negative terminal of the battery is at the same potential. So the capacitor is said to be fully charged with a potential difference V and Q charge stored. So now in our next lecture we will study different configurations of the capacitor and will find out capacitances for different configurations.